Hello again. Today I'm going to show you how to do a single sample t-test in Excel. Now remember, we're going to do a single sample t-test when we have a population mean, but we don't have a population standard deviation. So remember, with the z-test, we had both the mean and the standard deviation. But sometimes that's just not possible to have both. And in fact, most of the time, we're able to get means quite readily. In fact, if you look at popular media, usually are given a bunch of averages, but rarely ever are you given standard deviations. And so in those types of situations, we have another statistical test that helps us out. It's the single sample t-test. And in this test, we estimate what that population standard deviation is going to be based on the sample of the data that we have. So if you haven't already, go ahead and open up the Excel spreadsheet in the directions below, and then we'll get right into an example. So let's start off today just taking a look at the directions. So once you open up that Word document, you're going to notice that step one is to get your descriptive statistics. Now, we're going to make one small adjustment to our descriptive statistics that we haven't done up to this point. Once we select our descriptive statistics, the dialog box will open up and there will be an option for us to check what's called a confidence level. We're going to want to check that for this particular analysis. And I'll talk more about that once we get there. Then in step two, we need to prepare the data for the analysis. This is very similar to what we did with the z-test. So remember, Excel didn't actually have a z-test for a single sample. It also does not have a t-test for a single sample either. And so we need to make a little bit of adjustment to trick Excel into thinking it's doing a paired sample t-test, when in reality we want it to give us a single sample t-test. Once we have our data prepared, then we'll go to our data analysis. We'll select the t-test for paired two samples for means. We'll fill in the necessary information in the dialog box, and then we'll get our output. And then just like before with our other hypothesis tests, the hypothesis test tells us the results at a group level, at an overall level. If we want to know at the individual level, then we have to continue on and do a couple additional analyses. One of those additional analyses is the effect size, so that's at the individual level. And then the final analysis is a confidence interval. And again, we get the confidence interval when we want to estimate what the true population mean is. Our sample mean that we get from our data is our best guess, but we know when the population is either going to be higher or it's going to be lower than that. It's not going to be exactly the same as our sample mean. So we create a range where we expect that population mean to fall. So let's take a look at the data set that we have here. Looks like we have a variable called media hours. We go down to the code book, we can get some more information about it. I've also placed a scenario in there as well to help us along in this analysis. Statistics always happens within context. So understanding how to apply our statistical analyses is particularly important. So it looks like our variable is media hours. It's the number of hours children watch shows and movies in a week. So let's take a look at our scenario here. In our scenario, it says a recent media report stated that the average American child spends 28 hours a week watching shows and movies. I'm going to stop right there just really quick. That gives us some information that actually is going to be a population mean that we can compare to. So on average, US children spend 28 hours a week. And so now, once we have that information, we can start taking smaller subsets of children and comparing it to that national average. All right, so that's where we're going to get our population mean. Let's continue here with our sentence. And so it says, and a recent research study found that children who participate in organized sports spend less time on various forms of media. All right, so that's going to be important. So we have some previous research here that tells us this is going to be a one-tailed test. In particular, it looks like children who participate in organized sports spend less time watching media. And so that's going to tell us that we're going to set up our critical region in the negative tail of the distribution. That means our critical value is going to be a negative number this time. All right, so looks like we would like to know if sports results in less media viewing in our local community. And so our local community is going to be our population of interest. We want to compare that population to the overall US population. And so we're going to infer our local community population based on a sample. So it looks like we're going to randomly select children from the local soccer league. And in this case, we can get a truly random selection here because the soccer league has the name of all the children that are enrolled in the sport. We can get a truly random sample from that. So it looks like once we get our random sample, we ask the parents then to report the number of hours that their child watches shows and movies during the previous week. And so we want to know, do children in our community watch fewer hours of shows and movies on average than the overall US population. Now, of course, we need to give ourselves some level of probability. To what degree are we going to say that there's a possible error? And it looks like we're going to say our type 1 error rate is going to be 5%. So that's an alpha of 0.05. So again, remember, an alpha is a probability. We multiply it by 100, it gives us a percent. So that means that at the end of the study, if we conclude that the children in our local community watch fewer hours of TV, then there's going to be a 5% chance that we could be wrong with that conclusion. So remember, with statistics, there's always a chance that we're wrong. We're never 100% sure, which is why we never say prove in any of our statements. We say support, or it looks like, or it appears, but we never say prove, because there's always a chance that we can be wrong. In this case, that's our type 1 error rate of 5%. So now that we have a better understanding of the question, let's go to our data. I'm going to click on that data tab at the bottom. And so we have our variable here. I'm just going to skim through it really quick. It doesn't look like we have any missing numbers or any empty cells here, but I'm still going to sort it just out of practice, so when it does matter, I don't forget. And so again, if we scroll down, we can see it doesn't look like there's any missing values here. All right, so let's take a look at our directions. And so the very first thing that we want to do is we want to get our descriptive statistics. Now remember, when we do this, we're going to check an additional box for the confidence level. We're going to go to data analysis. You know how to get descriptive statistics. We'll put in our range of values. That's going to be column B. We do have labels in that very first row, so I'll check that box. We want our summary statistics, and then right below summary statistics, you're going to see this confidence level for mean. We're going to check that box. Now, the next thing we want to make sure is that the percent is set to what it needs to be. And here it says a 95% confidence level. So if our alpha is 0.05, we're saying there's a 5% chance for an error. So if there's a 5% chance for an error, then that means that we're 95% confident. So in other words, 100% minus 5 is 95%. If our alpha was 0.01, then there'd be a 1% chance for an error, and our confidence level would be 99%. So make sure you take a look at your alpha, make sure you take a look at that type 1 error rate, make the adjustment to the confidence level as you need to. In this case, it defaults at 95, which is what we want here. Our alpha is 0.05, type 1 error rate is 5%, so our confidence is 95%. All right, so that's going to do some of the calculations for us when it comes to getting our confidence interval. And when we get to that point in this video, I'll show you how that works. So go ahead and check your output, and let's put it someplace on our data set. Give yourself a little bit of space in your spreadsheet. So I'm going to put it in G2, and I'm just going to click OK. All right, and so there are our media hours. Again, you'll see our mean. We'll have a standard deviation. Notice that there will be reported standard error as well. And then notice down here we have accounts, and then our confidence level that we ask for as well. So be able to report what you need to out of this table when it comes to your assignments and your exams. So if we go back to our directions, the next thing that we need to do, we need to prepare our data for a t-test. And again, there is no single sample t-test in Excel, but we can mimic one if we create a second column and we just put in that population mean. So notice this is just like what we did with the z-test. The only difference here is we're not doubling the data. So remember, z-test, you double the data, then create your column for the population mean. But with a t-test, all you're going to do is create your second column with the population mean. You don't need to double the data set here because the path that we're using for analysis is a paired two-sample for means. It's a dependent samples test, in which case we don't need to double the data set. Let's go back to our spreadsheet. Let's put that column in here. I'm just going to type pop mean for the population mean. And if we look at our scenario, it looks like that population mean, again, is 28 hours a week. So we're going to put 28 there. And I'm just going to drag that 28 down so that I have a pair of values for every observation, the reported value and then the population mean. Now that we have that second column, our data is ready to go, is prepared and ready for a t-test. So we're going to go to our data tab, click on data analysis, and we're going to select the t-test for paired 2 samples for means. Data analysis. If you scroll to the bottom, you're going to see your t-test. The one that we want is the t-test that says paired 2 sample for means. We'll click OK. Again, we'll have to select our variables, our numbers. So variable 1 is going to be our sample data. Variable 2 is going to be that population mean. So that's column C. Our hypothesized mean difference is going to be 0. So remember, that's just like with the z-test, it's based on the null hypothesis. So if the children in our local community spend the same number of hours watching TV as the US population, then the means would be the same. And if we subtracted them, we would get 0. And so that's our null. We're assuming that nothing is going on until we have enough evidence to suggest otherwise. And that evidence is going to come from our statistical analysis. So we'll put 0 in there. That's based on our null. We do have labels in the first row, so we'll click our labels box. We're going to leave our alpha at 0.05. Remember, that's the alpha in our scenario. We have a 5% chance for a type 1 error. I'll click on my output range, and I'm just going to place it right below my descriptive statistics. And I'll go ahead and click OK. All right, so there's our output. Let's take a look at it here a little bit. You'll notice that we have our means. So it looks like the mean of our sample of children in our local community. The average number of hours that they're spending watching media looks like it's 23.62. Again, we know that the population mean is 28. It also gives us our observations. Our observations there as well. We also have our degrees of freedom. And so remember, the degrees of freedom are the number of values that are free to vary infinitely. So if you go back to that narrated PowerPoint, talk about why we use degrees of freedom when we're estimating the population standard deviation from the sample data. We then have our t statistic. Looks like it's a very large number. It's a negative number. We would expect it to be negative because our mean for our sample is less than the mean for the population. So we would expect a negative value there. That's perfectly normal. And then notice we have our critical values. We have a critical value for a 1-tailed test and a 2-tailed test. Now, based on our scenario, we have a 1-tailed test because we have research that shows that children who participate in organized sports spend less time on media. And so because it's less time, we expect that the values are going to decrease. So we're setting our critical region in the negative direction. So it's going to be a negative critical value. Just remember that when it comes to your output, the value that you get for your critical value is always going to be positive, because Excel doesn't know when it's negative or when it's supposed to be positive. The sign of the critical value is a conceptual matter, not a mathematical matter. So in this case, this would be a negative 1.66. So whenever doing a hypothesis test, I always highly recommend that you draw out your distribution, that you create your critical region so that when you put in your test statistic, you're making the correct statistical decision. So I'm going to go ahead and draw that distribution. So here's my normal distribution. So the t distribution is still a normal distribution. It's still centered at 0. And so we're going to go ahead and put in our critical value. Here it's negative 1.66. And again, remember, it's negative because our previous research says that children who play sports spend less time, so it's going in the negative direction, less time watching media. So I'll put my critical value equals negative 1.66. All right, and then I'm going to take a look at my test statistic. In this case, I get a negative 11.1. That's going to be really, really far away from my critical value in the negative direction. That's someplace way out over here. And that's where we're going to reject the null hypothesis. So remember, everything in the shaded region is where we make the decision to reject the null. Anything that's not shaded will be our decision to fail to reject the null hypothesis. So again, our null hypothesis here is that there's no difference in watching media between those in the local community and those in the US population. So here it looks like, based on our test statistic, it looks like we're going to reject that null hypothesis. It looks like we're finding support for that the children in our local community who are playing sports are indeed spending less time watching media than the overall population. And so that would be our statistical conclusion. And remember, that is at the group level, it's not at the individual level. I can just say children overall in my local community. I can't really talk about my child. I can't talk about my daughter, Katie, and say that she's going to spend less time on social media, because a hypothesis test is at a group level, not at an individual level. So that leads us to our additional analyses. So if you go to our directions page, we're going to scroll down here. We're going to go down to where it says the effect size. Remember, the effect size is at the individual level. So I know overall, it appears that children in my local community who play sports are viewing less television or less media than the overall population. What I want to know is, will this practically impact an individual child, such as, let's say, my child, my daughter, if she was playing sports, would I be able to reasonably conclude that she would watch less media and spend less time watching TV and watching shows and movies? So to find that out, I need to conduct an effect size. I'm going to go back to my spreadsheet here. I'm just going to go right below my table, and I'm going to type in effect size. Remember that effect size formula is that we're going to take the sample mean, that's M. We're going to subtract the population mean that was in our scenario, that's 28. And we're going to divide by the standard deviation. And we have that standard deviation in our output. So hit equals. I'm going to open parentheses here because I want to get my subtraction first. I'll click on the mean for my sample based on the local community. I'll subtract the population mean of 28. I'll just click on that cell as well. I will close the parentheses. Then I'm going to press the /, which is going to tell Excel to divide. Then I'm going to scroll up. I'm going to find my standard deviation in my descriptive output. And I have it right here. It looks like it's 3.49. And I'm just going to hit enter, and that's going to be my effect size. It looks like it's a very large effect. It's negative 1.26. Don't let it fool you. You can have values greater than 1 or less than -1. Additionally, don't be alarmed that it's a negative value. All that negative is saying is that our local community, or children in our local community, are viewing less shows and movies, less media than the overall population. So it's going in the negative direction, showing less than whatever it is that we're measuring. Now, don't forget your conventions. So again, an effect size around 0 is no effect. Around plus or minus 0.2 is a small effect. Plus or minus 0.5 is a moderate effect. And plus or minus 0.8 is a large effect. Here, negative 1.26 would be a very large effect. So this tells me that I can expect that an individual child, such as my daughter, if she's playing sports in the local community, that she's going to be watching a lot less media than an individual child in the overall U.S. population. So not only do we find in this particular analysis that there is a difference at the group level, local children playing sports are watching less media than the overall population, but also conclude that this will practically impact an individual child. That an individual child in my community who's playing sports will be watching less media on average than an individual child in the overall population. So I find support at the group level and also at the individual level. So if I was to write this out, I would say that we would expect that any individual child in the local community who plays organized sports will watch 1.26 fewer hours of media than an individual child in the overall U.S. population. And I would say that this is a large effect. And again, that's if I was to write it out. So just make sure you go back to that narrated PowerPoint. Make sure you understand what 6 things you need to include in your effect size explanation. I just covered them all in that explanation of the effect size. All right, so we have one more analysis to do. We have to get our confidence interval. So again, the reason why we're getting that confidence interval is because our average for the local community of children watching media is 23.62 hours a week. That again is our best guess, and it's based off of our 78 children, our 78 observations. There's a lot more than 78 children in our local community. All I had was a sample of the data. I did not have the full population. So that means I'm estimating based on those 78 children, which means that my estimate, 23.62, could be off, and chances are it's going to be off. And so we want to create a range of where we would expect the true population mean to fall for our local community of children. To get that confidence interval, if we go back to our directions page, you're going to see that there is formulas down here. We'll need that standard error if we're to use these formulas here. I'm going to show you a shortcut. So if you're to do it the long way, you need to calculate that standard error, which is just the standard deviation divided by the square root of the number of observations, or the count in your sample. Once you have that, you can plug that into your formula, and you can multiply it by the two-tailed critical value. So for the lower bound, we'll take the negative two-tailed critical value. For the upper bound, we'll take the positive two-tailed critical value. So here's where I'm going to show you the shortcut. So you can do it the long way and use the formula, adding the mean of the sample to both the lower and upper bound, or we can use the confidence level that's in our descriptive statistics to shorten a little bit of our analysis. So remember, when we got our descriptive statistics, we got this confidence level. We checked that box. So what that's going to do for us is that it's actually going to do the multiplication for us already. So it's going to take the critical value and multiply it by the standard error. So all we have to do is take that confidence level, subtract it from the mean for the lower bound, and add it to the mean for the upper bound. Essentially, that confidence level is doing this part of the math for us. So then all we have to do is add and subtract it to the mean. So let's go back to our spreadsheet here. So we're going to get the 95% CI, or confidence interval, and it's 95% again because our alpha is 0.05. There's a 5% chance for an error. And we're going to need to get a lower bound, and we're going to need to get an upper bound. Now again, you are free to use the formula in the long version if you like. I'm going to show you the shortcut. If you do use the long version, it works just like it did with the single sample z-test. So you can go back to that lecture and remind yourself how to do it. To show you that shortcut, I'm going to click on the cell that's next to the cell that has lower in it for the lower bound. I'm going to hit equals. And again, just as a reminder, we want to make sure we select the mean of the sample, not the mean of the population. We know what it is in the population in US. What we don't know is what the hours of media viewing a week is for the local community. Our best guess is for the 78 children in our sample, but we don't really know what it is for the local community. So we're going to center our range for this confidence interval around the sample mean. Once I've selected that sample mean, I'm then going to press my negative sign for subtraction. And then I'm going to scroll up to my descriptives, and I'm going to press on that confidence level cell and select it. And then I'm going to hit enter. And so what that did is it took our mean of 23.62 and it subtracted the confidence level of 0.79. Remember, that confidence level is just the standard error times the negative t critical value for a two-tailed test. And remember, confidence intervals are always two-tailed, regardless if your hypothesis test is one-tailed. So that gave us a value of 22.83. And so that's our lower bound for the number of hours that children in our local community are watching media. All right, so let's get the upper bound. It's going to be very similar. We're going to hit equals. We'll click on the sample mean, 23.62, but this time I'm going to add that confidence level. I'm going to add 0.78, I'll hit enter, and it looks like I get 24.40. So it looks like my 95% confidence interval is 22.83 for the lower bound and 24.4 for the upper bound. So if I was to interpret that and to write it out, like I'll ask you for an assignment and for an exam, I would say that there is a 95% chance that the true population mean for the number of hours children in the local community watch media is between 22.83 and 24.4 hours. So again, our best guess based on the sample for the local community was 23.62. But in the population, I know it's not going to be exactly that value. It could be less than that. It could be more than that. But I can say that I'm 95% confident that it's going to be between 22.83 and 24.4 hours. So that's it. That's everything for a single sample t-test. Don't forget to upload your spreadsheet below. Make sure you put your name as the file name. And then I hope you have a good rest of your day.